Hello lamai. Let's start the discussion about the reactions of D block cations. Right? Okay. To begin with, before coming up with the reactions of D block cations, you should know the colors of the aqueous solutions of these D block cations. Right? No need to know about all the cations coming up with all the elements of the D block stuff. But basically, you should know about the cations which will be formed by the D block elements, basically 3D elements, actually from chromium to onwards, and some of the other 3D elements, which are actually the cadmium, mercury, and silver, right? Other than the elements appearing in the 3D row, you need to know only about the cadmium, mercury, and silver when it comes to A-level syllabus, right? Okay, so let's first discuss about the colors of the aqueous solutions of these 3D cations, right? Okay, so colors of aqueous solutions. Right, as I have told earlier, we are not going to discuss about the scandium, titanium, and vanadium chemistry in our A-level syllabus. We are discussing about the chemistry of elements from chromium to zinc at the 3D row, right? Okay, so we should know the colors of those aqueous solutions then. So the color of Cr3 plus aqueous, right? The color of Cr3 plus aqueous actually coming up with two colors, right? If the solution is neutral, the Cr3 plus aqueous is actually purple in color. If the solution is acidic, that means the pH is less than 7, then your Cr3 plus aqueous solutions are green in color, right? Then you have the manganese 2 plus aqueous solutions. Manganese 2 plus aqueous solutions are colorless, one can say colorless, or very pale pink. If you had written the color of manganese 2 plus aqueous as pink, you are wrong. It can be referred to as pale pink or normally the colorless, right? So when it comes to iron, the Fe, you have two cations coming up with the iron, Fe2 plus aqueous as well as Fe3 plus aqueous, right? If you are referring to colors of these things, the Fe2 plus aqueous solutions are greenish, right? Green in color. One can say light green. And Fe3 plus aqueous solutions are actually yellow brown in color. Fe3 plus, so this is the Fe3 plus. Those solutions are coming up with yellow brown color. Yellow brown, right? So what about the other guys, right? Then you can think of the color of cobalt 2 plus, nickel 2 plus, copper 2 plus, zinc 2 plus, right? It comes to colors. Cobalt 2 plus aqueous solutions are pink, nickel 2 plus aqueous solutions are green in color. Copper 2 plus aqueous solutions are light blue in color. And zinc 2 plus coming up as a colorless solution. Right? The color of the copper sulfate aqueous solution is due to the presence of Cu2 plus ions, right? Remember that. Okay. And if you are regarding to the colors of few other D block cations, right? So we can think of the color of cadmium 2 plus, mercury 2 plus, as well as silver plus. All of these things are coming up as colorless solutions. Colorless solutions. So some theory to mention here, Lamai. So basically, if your cation is coming up as a D10 configuration, coming up with the D10 configuration, if your cation considering coming up with a D10 electronic configuration, then those aqueous solutions are colorless, right? All of these guys are coming up with D10 electronic configuration, right? Zinc is kind of S2D10, zinc 3, right? 4s2 3d10. So 2 plus means the 4s2 electrons are removed. That means just the 3d10. This guy coming up with 5s2 4d10. So as the 2 plus ion is formed, right? It is going to be just the 4d10 is remaining. So if your cation coming up with the d10 configuration, even this one here with the silver, it is 5s1 4d10. So we conceal the plus, its configuration is just 4d10, right? 4d10. So D10 configuration. If your cation is in the D10 configuration, their aqueous solutions are colorless, right? So that is the point there. So it is easy to remember the colors of cations containing D10 configuration, right? Those are colorless. So you can mention that thing. This is because of D10 configuration. Mention that in your note, right? This note is there at the page number 6 of your dude, right? Just put these colors, right? Where this one is coming up with D10 configuration, those aqueous solutions are colors. So the colors of these aqueous solutions should be known before studying anything further, right? Okay, so these are clear, no? The Fe2 plus and the Fe3 plus. Right now, just put these colors, right? Just color these things, right? In a note at the page number 6 at the table. These things are mentioned. These are all about the aqueous solutions, right? So just color this stuff. CR glass is purple or green according to the right acidic or neutral nature. The color varies for the CR3 plus aqueous. So manganese 2 plus is pale pink or colorless. If Fe2 plus is green, F3 plus is yellow brown. So I'll write it here, green. This is yellow brown. Just color like that, half with yellow and the other half is brown, right? This you can use the light green color, and this is colorless, right? One can say pale pink. Right now, just complete those things, right? There is no way to remember these colors of the aqueous solutions actually, but I'll provide some easy methods to remember the colors of the hydroxide precipitates, amine complexes as well as the chloride complexes, right? Okay, right. This color name, right? After studying these colors of aqueous solutions, let's move towards the colors of hydroxide precipitates. Hydroxide precipitates, right? Okay, that's the next stuff. So basically, colors of hydroxide precipitates, right? Colors of hydroxide precipitates. Right? This is about those things. Lamai, if you have to add some NaOH or kind of a base, it could be supplied by the NaOH, kind of a strong base, KOH, BaOH, to kind of strong bases, or even you can provide these OH minus ions to precipitate the hydroxides by adding some aqueous ammonia as well. Right? If you had supplied some OH minus ions, aqueous OH minus ions to the solutions containing these cations, all of these guys are capable of forming the hydroxide precipitates, right? Capable of forming the hydroxide precipitates, right? Let's discuss the colors of those hydroxide precipitates, right? So, if you have to supply some OH minus ion, right, in the form of NaOH or aqueous ammonia, you can supply the OH minus ions to the medium, right? See what will happen, right? So I'll write it here. OH minus ions can be supplied to aqueous solution with the use of NaOH, kind of any strong base, or aqueous ammonia acid, right? So aqueous ammonia, we know it's a base, so capable of providing OH minus ions solution, right? So let's see what will happen if you have to provide some OH minus ions to these solutions. And basically, the hydroxides will form. Normally, when it comes to the colors of hydroxides precipitates, when it comes to colors of hydroxide precipitates, those are basically, right, coming up with the colors of the aqueous solutions. Those will follow the colors of aqueous solutions. Basically, the hydroxide precipitates will follow the colors of aqueous solutions, but with some intense nature. Some dark colored stuff will be appeared, but basically following the colors of the aqueous solutions. See, if you need to know, it's like this. If you are coming up with the Fe2 plus, it is light green in color. So when you are adding some OH minus there, you will form kind of precipitate, which is dark green, right? What is the precipitate? That is FeOH2. This is the hydrogen precipitate coming from the 2 plus sign, right? 2 plus sign. I write it as dark green. So if you are to add some OH minus to the Fe3 plus aqueous solution, what will happen? The Fe3 plus aqueous solutions are yellow brown in color. So the forming FeOH3 hydroxide precipitate is going to be kind of red brown, So following the color of the aqueous solution, but some dark nature with the color, right? So what about these? Cobalt 2 plus will give you cobalt hydroxide. So what is the color? As copper 2 plus aqueous solutions are pink in color, this guy is also pink. Cobalt hydroxide precipitate, right? Okay. For the nickel, we form a nickel hydroxide precipitate. As nickel 2 plus aqueous solutions are green, this is also green. One can say dark green or green. Here copper 2 plus aqueous solutions are blue in color. So that copper hydroxide precipitate formed when you are adding some OH minus ions to the solution will be just blue. This is light blue. This becomes just blue. So as D10, D10, D10 guys are colorless. The solutions are colorless. They are precipitates are also without colors. So a precipitate without a color can be considered as white. Can be considered as white, right? For these guys as well. If you are adding add some OH minus, right? Basically, first form the whitish precipitate. So normally hydroxide precipitates follow the colors of aqueous solutions. That is what you should note that here, right? Then, yeah, let's put these two stuff as well. Right? So the two things are mercury hydroxide, white, and silver hydroxide is also white. Right? Okay, this is the normal nature. And some special things will occur with the mercury and silver, as those are unstable. The hydroxides are unstable because those are inert metals, no? Mercury and silver. So they are keen to be alone, right? They are not that much keen to gather with the other atoms. They are very keen to be alone, right? So the hydrogens will be released and ultimately convert to the oxides there. Convert to the oxides there. As soon as the hydroxide is produced, those will convert to the oxides. And those oxides are coming up with some different colors, right? So the oxide of mercury is yellow, some special color there, is yellow. Oxide of silver, the silver oxide, Ag2O, is actually brownish black, brownish black. Brownish black, right? So can't you see that? Right? So that is the normal trend. The hydroxides will follow the colors of aqueous solutions, right? Okay. Then we have two special guys, two special hydroxides, actually, which are not following the colors of aqueous solutions. Let's discuss about those two guys, right? So when it comes to chromium, even though the chromium 3 plus solution is coming with purple and green, the chromium hydroxide precipitate is actually blue-green. The chromium hydroxide precipitate is actually blue-green, right? Blue-green in color. And when it comes to manganese, even though the manganese solution can be referred to as pale pink, its hydroxide coming up as kind of yellowish white, yellowish white. So basically, those are the only two occasions where you observe kind of a color which is not actually following the colors of aqueous solutions. Otherwise, when it comes to hydroxides, they follow the colors of aqueous solutions, right? So it is not hard to remember the colors of hydroxides, precipitates, because those will follow the colors of aqueous solutions. But only for the chromium and manganese, some other colors will appear. Just study those two things, right? Okay, just color the stuff in a note. Remember, these OH minus ions can be provided by any kind of a base. It could be a strong base like NaOH, KOH, rubidium, any kind of a group 1 hydroxide, right? Or it could be provided by the ammonia as well, as ammonia is kind of a weak base, right? Okay, let's complete the colors. Right. Okay. After studying the colors of the hydroxide precipitates, let's go towards the next section appearing with your table. That is all about the colors of amine complexes which can be formed when adding excess ammonia to D7 to D10 cations. This is about that thing there, right? The colors of amine complexes. This is the major discussion here with the third column with you, right? Basically, it's, yeah, with the third column, right? So basically, now we are going to discuss about what happens when you add some ammonia, right? Products formed when excess of aqueous ammonia is added. Okay. Lamai, if you add even excess ammonia to solutions containing metal cations other than the D7 to D10, other than D7 to D10, we are not expecting to observe the amine complexes forming. Instead of that, the hydroxide precipitate will appear because all the 3D elements are capable of precipitating the hydroxides. So when it comes to hydroxide precipitating pattern, it says at the S block only the beryllium and magnesium, those two cations will precipitate hydroxides. But when it comes to P and D block metal cations, all of them are capable of precipitating the hydroxides when the OH minus are provided to solution. Right? That is the theory behind the hydroxide precipitation. So, if you were to add some ammonia, first of all of these 3D elements, all of these 3D cations will form the hydroxide precipitate. Right? If some excess ammonia is added, if you add some ammonia further to those so precipitated hydroxides, the D7 to D10 cations, only those things, D7 to D10 cations are capable of converting the hydroxide to the amine complexes, right? So if you are dealing with a cation not below D7 D10, excess of ammonia will give you the hydroxide precipitate. But if you are concerning a cation which belongs to D10 group, then those will form the amine complexes when you are adding excess ammonia, right? So the special thing at the third column in your table at the page number 6 is about that, right? So the amine complexes can be formed by D7 to D10 cations, right? This concern about those things. You can think of cobalt 2 plus, nickel 2 plus, copper 2 plus, and zinc 2 plus. Other than the 3D guys, you can think of cadmium 2 plus, mercury 2 plus, as well as the silver plus. These three guys also belongs to D10 category. All of these are D10 cations, right? These are D10 cations, and this is D9. So D7 is D8, and this is D9. So these are capable of forming amine complexes. Let's see how the colors will vary. Remember, all the amine complexes are coming up as solutions. The hydroxides are the precipitates, but all the amine complexes are coming up as solutions when you're adding excess ammonia. You are capable of producing amine complexes, which are solutions always to these D10 cations, right? So let's come up with those structures, right? So cobalt, coming up with cobalt amine complex. Nickel, coming up with the amine complex. The first two guys coming up with two sixes. Remember the cricket match, right? Okay. So copper and zinc will have 4 amine ligands, while the cobalt and nickel having 6, right? Copper and zinc will have 4 amine ligands in their amine complexes, right? So for these stuff, right, this cadmium, sorry, right? So these guys are also capable of forming amine complexes, right? Cadmium amine complex coming up with 4 amine ligands. Mercury amine complex again coming up with 4 amine ligands. Cadmium and mercury are the two elements which is coming under the same group as the zinc, and when it comes silver, it will form an amine complex with just 2 amine ligands, right? So if you are regarding the colors of these guys, as all of these guys are D10 complexes, all of these guys are D10 cations, complexes contain D10 cations, all of these guys are colorless, right? D10 cationic solutions are colorless. D10 cationic solutions are colorless. Even solution, even the complexes. But if you are not a D10 situation, not coming up with a D10 situation, you have a color. Let's discuss about colors as well, right here. So cobalt amine complex coming up as a yellow brown solution. Nickel amine complex coming up as a blue color solution, and copper amine complex coming up as dark blue solution. Those are the colors of amine complexes, right? Which is at the third column of the page number 6, right? Just color those stuff, Lama. Remember, all the solutions contain D10 cations. D10 cations, even it is kind of in a complex form, still those are coming up as colorless solutions, right? No? Okay, just complete this one. Just put those colors in your note. Right. Next up, let's discuss about the colors of chloride complexes, which will form when you are adding some excess of Cl minus ions to solutions containing these cations, right? Okay. So our next discussion is about the colors of chloride complexes, right? Those are the kind of complexes which can be seen with almost all the right D block cations, right? So colors of chloride complexes. These are the products formed when excess of Cl minus is added. Excess of Cl minus, or that can be provided by conc HCl as well, is added, right? Let's discuss what will happen. So you have chromium 3 plus, manganese 2 plus, Fe 2 plus, Fe 3 plus. Then you have cobalt 2 plus, nickel 2 plus, copper 2 plus, and zinc 2 plus. Normally in our syllabus, we are concentrating on the chloride complexes formed by 3D cations, right? Let's see what kind of chloride products can be obtained by adding excess Cl minus, that can be added by conc HCl. So basically, Lamai, we have two special chloride complexes. We have two special chloride complexes in the form of chromium and the cobalt. The two chloride complexes coming from these two are special. Other than that, all the chloride complexes are coming up with 4 chlorine ligands now. 4 chlorine ligands. Actually, basically, other than the chromium 3 plus, all the other chloride complexes are coming up as containing 4 chlorine ligands. Right? Let's write that those things. So we'll discuss the colors later. All are coming up as 4 chlorine ligands. It means Cl4 2 minus, FeCl4 2 minus. Right here, FeCl4, it is just minus. How to come up with the charge of this thing? Basically, Cl minus coming up with minus 4 and Mn plus 2. Minus 4 plus 2, the summation is represented here. Minus 4 plus 2 is minus 2. Again, minus 4 plus 2 of Fe2 plus gives you minus 2. Here, minus 4 with the 4 chlorine Cl minus ions and plus 3 with the Fe here, the Fe3 plus ion. So it should be minus 1. Right? So other than this chromium stuff, all the guys are coming up as 4 chlorine ligands. So cobalt Cl4 2 minus, nickel Cl4 2 minus, copper Cl4 2 minus, and zinc Cl4, 2 minus. Then what is special about this zinc? It is not coming up with a Cl4 ligand, Cl4 kind of complex. It will be like chromium Cl6, that is special. It's 3 minus. Cr3 plus n with 6 of Cl minuses, 6 minus there, 3 plus is there, so summation is minus 3, right? So chromium is special as it is giving you a complex with 6 chlorine ligands, right? That is to be mentioned. And then when it comes to colors of these complexes, the chromium and cobalt guys are special. Chromium and cobalt guys are special, right? What is the specialty? Those are with colors other than the yellowish color. Those are with colors other than the yellowish color. Then what is the specialty there? The specialty is actually when it comes to other guys, other than the colorless zinc 2 plus, other than the colorless zinc 2 plus, it comes to other colorful chloride complexes. Those are actually kind of yellowish. So when we are referring to these colors, as this one is coming up as a D10 cation, we always know that D10 aqueous solutions are colorless. So this one is colorless. No worries with that. And other than these two special guys, all the other colorful product complexes are yellowish, right? That means this one is yellow in color. This one is yellow in color, right? This one is yellow in color. This one is yellow in color. Yellow solutions, right? And when it comes to this one, it is also yellowish. Now we say it as greenish yellow, or yellow green, right? Yellow green. Or one can say greenish yellow, right? So if they have asked you the color of manganese chloride complex, if you have written it as yellow green, that is correct. If you have written it as yellow, just the yellow, it will be also marked as true, correct. But if you had written it as just the yellow, then you won't get marks, right? So what you should mention here, what you should remember here is, other than the chromium and cobalt, all the other colorful chloride complexes are yellow in color, right? Yellow in color. See, this guy is colorless, right? That is colorless. It's very clear because the detailed configuration, right? Right. Then what are the colors of these two guys? These two guys are special. What are the colors of them? The two special guys, right? The colors of these guys. This guy is blue purple or blue violet, and this guy is just blue. So these two guys are very special. Huh? In this sense, these two guys are very special. Just box those two guys. Just box those two in your table. Right? Just box those two. And we know that tinting is always colorless, but all the others will come up with a color related to yellow. Right now? So complete this stuff as well. Right. Okay. After this, right, we'll discuss about a few other common reactions which you can see with the D block tables, right? So we are done with the page number 6. So page number 7, 8 and 9 is all about the reactions involved in these metals, basically from chromium to copper, those 6 metals, right? So when you are going through those tables of reactions, right, some common reactions are appearing. Some common reactions are appearing with most of the elements. So first, let's discuss about those common stuff other than these, right? These are all of these things are what we have discussed up to now is common for all of these 6 tables. Other than this, right, let's discuss about what are the common reactions available with these tables before studying the reactions, right, one by one, right? Okay, right. So let's discuss about some other reactions involved in the D block tables, right? Some other common reactions appearing in these tables, right? Okay. Now, actually with these D block tables, right? You can see the oxidation state. You can see the oxidation state of the corresponding element in your compound or ion at the left hand side of your table. So when it comes to chromium, you see 0, plus 2, plus 3, plus 6. Those values are the oxidation states of those interested element, right, in those compounds, right? And with the manganese here as well, 0, plus 2, plus 4, plus 6 and plus 7 are available. So those are the oxidation states of manganese in those single species, right? With the iron, you can see 0, plus 2, plus 3, like that. So with all the tables other than copper, you would see the numbers start from the plus 2. The numbers start from the plus 2, right? Other than copper, with all the tables, you will see the numbers start from the plus 2. So plus 2 cation, right? So basically, you can convert your metal, the metallic form, to that plus 2 aqueous cation or plus 2 aqueous ionic solution by just simply adding some dill acid. By just simply adding some dill acid. So you can see that thing with each and every table other than copper. We'll discuss what happens with the copper as well, right? But other than copper, you can see that specific reaction appearing with all the other 5 tables. So what is the reaction? So the reaction is, right, metal reacting with a dill acid to convert the metal to its salt, that means the ionic form, right? Ionic form, salt. It can be referred to as a salt and H2 gas. This is that reaction we are discussing about, right? So this thing will be true for any metal above hydrogen in the activity series. For any metal above hydrogen in the activity series, this kind of a reaction is possible. What happens with the copper is actually, copper is below the hydrogen activity series, right? So copper is unable to do this kind of a reaction, but other than copper, all the other elements we are discussing here are above hydrogen in the activity series, right? So all of those will participate in this kind of reaction and convert the metal to the nearest oxidation state, right? The 2 plus cation, right? So with all the guys, we are capable of seeing this, right? So basically, converts to 2 plus cation, right? So if you know the examples, you need some examples, right? You see, with chromium, with the addition of DLH plus, it can be provided by DLH2SO4, DLHCl, right? Chromium turns to Cr2 plus aqueous, right? So let's put the colors of those things as well. So Cr2 plus aqueous is light blue, light blue, light blue in color, right? Then you have the manganese. So if you add some DLH plus, it will convert to manganese 2 plus aqueous solution. You know the color there. You know the color there, right? So manganese 2 plus aqueous solutions are colorless. You see them in your tables, right? The metal can be converted to the plus 2 oxygen state, the plus 2 aqueous ion, by just adding a DLH plus. That is what we are referring to here, right? So Fe2 plus, sorry, Fe can be converted to Fe2 plus form, Fe2 plus form, the nearest oxygen state available there, by just the addition of a dill acid, DLH2SO4, DLHCl, right? Fe2 plus is green in color, right? Light green in color. So cobalt and nickel as well. All of these guys can be converted to the its 2 plus ion. With the addition of DLH plus. See those things in your tables, right? So, that is kind of a common reaction scheme for all these elements, right? Cobalt 2 plus is pink in color, nickel 2 plus is green in color, right? Okay. So just see those reactions and color the species, these aqueous ionic solutions in your tables. Right? Just go to the tables and color them. So from chromium to chromium 2 plus, that conversion can be done with the addition of DLH plus. Just color the chromium 2 plus aqueous solution as light blue. Otherwise, normally the aqueous solutions are written as normally the right in plus aqueous solution can be written as M H2O6 2 plus, right? With D block chemistry, we are normally writing the aqueous solutions with some 6H2O ligands. That is what you are seeing there with all the tables, right? So chromium metal can be converted to CrH2O6 2 plus, right? By just the addition of a DLH plus. Just color the CrH2O6 2 plus with light blue in color at the chromium table. Then come to the manganese table. At the bottom, you see this reaction. Manganese solid, the metal, can be converted to MnH2O6 2 plus. MnH2O6 2 plus aqueous solution, which is colorless or light pink, and that can be done by adding a DLH plus, dill acid. DLH2SO4, HCl will be enough for that. Just color that Mn2 plus aqueous or MnH2O6 2 plus, that with pale pink or colorless. One can see it's pale pink as well, right? Next one, the Fe. So come to the Fe table, ions table, right? There you see this reaction at the bottom. The Fe metal can be converted to Fe2 plus ion, aqueous ion. That means FeH2O6 2 plus, FeH2O6 2 plus, by just adding a dill acid, DLH plus. Just color that FeH2O6 plus with light green in color. Right? Next, come to the cobalt table. Table belongs to the cobalt. There you will see at the bottom the cobalt solid, the metal, can be converted to cobalt 2 plus aqueous. That means cobalt H2O6 plus by just the addition of a dill acid, dill H plus. That solution is pink in color. Just color that with the pink color. That ball, just color with pink in color, pink color. Right? Okay. Next, go to the nickel table. Nickel table. There, you see this reaction at the bottom. Nickel solid metal can be converted to nickel 2 plus aqueous. So one can say nickel H2O6 2 plus aqueous, right? So by an addition of a dill acid. So the color of the nickel H2O6 2 plus complex is green. Green. Just color that with green, that ball, appearing with the nickel H2O6 2 plus. Right? So these things can be done with metals, 3D metals, other than copper. With copper, you won't see such. With copper, you won't see such. Right? Conversion of copper solid to copper 2 plus can't be done with a dill acid, right? Because copper is situated below hydrogen activity series, right? So this kind of reaction won't be occur with the copper, right? If you are thinking of copper, to convert the copper metal to copper 2 plus aqueous, to convert the copper metal to copper 2 plus aqueous, or copper H2O6 2 plus, which is kind of light blue. To do this conversion, you need a oxidizing agent. You need an oxidizing agent. With copper, you can't think of this kind of conversion just by a dill acid. You need an oxidizing agent, right? So the reason is copper is situated below hydrogen activity series. So this can be done by any metal above hydrogen activity series. Here, the metal should be above hydrogen in activity series. To convert it into a 2 plus aqueous ionic solution. So that copper can't do so. Right? Other than in copper, you can see this trend with all the other right elemental tables. Right? Just complete this stuff, right? Right. There is some common right reaction scheme available with each and every table, right? Okay, next one. Right? Another common kind of a reagent is there, like DLH plus. Another common kind of reagent can be seen here and right there, right? I mean, again and again in these tables, right? This is about that thing as well, right? The next one. With each and every table, actually not coming up with the copper and the nickel, but with other tables rather than copper and nickel, you would observe the H2O2. You would observe the H2O2 appearing with all of those tables, right? So this is just about that thing. H2O2 as a oxidizing agent. See, right? With chromium chemistry, we see this reaction. See, at the right hand corner. See, chromium hydro, CrOH4 2 minus. This thing can be converted to CrO4 2 minus aqueous ions. can be converted to CrO2 minus aqueous science by adding basic medium H2O2. Just see that reaction. Just see that reaction at the chromium table. Just observe that reaction. So what will be the color change? Right? What will be the color change there? So this guy is kind of greenish. This guy is kind of greenish. Actually dark green, right? This is actually dark green. The dark green. And CrO2 minus coming up as a yellowish solution. Okay, as a yellowish solution, right? So put those colors and observe that reaction at the chromium table. See. So the plus 3 oxygen state here of chromium, the plus 3 oxygen state of chromium can be oxidized to plus 6 oxygen state. This oxidation, increasement of oxidation state can be done by H2O2. H2O2. Right? See the usage of H2O2 in these tables. Right? H2O2 can be used to oxidize the metals in these species. In all the tables other than nickel and copper, you would see right this usage of H2O2. Right? So let's go towards the manganese table. With the manganese table, the MnOH2, that solid, right, which is yellowish white, actually can be converted to MnO2, can be converted to MnO2 solid, which is dark brown or brownish black, by just using H2O2. Now, this can be done by air oxidation as well, right? This conversion of plus 2 to plus 4 can be done by ArO2 as well, right? So that process can be speed up by adding H2O2, right? This can be done by ArO2, air oxygen. It is going to be a slow process. All these slow processes which are done by the ArO2, air oxygen. So 21% of the air is containing oxygen, right? So oxygen can be used to oxidize the other species. Oxygen is very keen of electrons now, so it can grab electrons from the other species and oxidize the other species, right? So that process normally happening with a very slow rate. So that thing can be speed up by adding H2O2. Reaction will be fast. So normally to convert MnOH2 solid to MnO2 by just allowing the air oxidation, just keeping it and exposing to air, it will take kind of hour or two. But if you need to do it at once, right, within 1 or 2 seconds, you need to add the H2O2. Actually H2O2 is capable of providing O2 minus to the medium, providing O2 gas to the medium. So H2O2 decomposes. With sunlight to H2O and O2, so that this O2 produced by this decomposition is capable of oxidizing the other species, right? So any process which can be done by any oxidation which can be done by air oxygen can be done by H2O2 as well, but in no time. In no time, right? Okay. So just copy the colors of MnOH2 solid as well as MnO2 solid in your manganese table, right? Okay. Let's discuss about the appearance of H2O2 at the table related to iron Fe. So basically, Lamai, FeH2O6 2 plus, the Fe2 plus aqueous solution, as well as FeOH2 solid, the precipitate, both these Fe2 plus forms the aqueous solution as well as the hydroxide precipitate, both can be oxidized in no time. So in no time if you are add H2O to those species. This thing is actually green in color, one can say light green, and FeOH2 is coming up with intense color compared to solution. So we can say green or dark green. Right? Those two things will be air oxidized slowly. These two things will be air oxidized slowly. But if you add some H2O2, that will happen very quickly. That will happen very quickly. So remember that any process involving air O2 can be done very quickly with use of H2O2. So FeOH2 6 2 plus will convert to FeH2O6 3 plus. The plus 2 will convert to plus 3 ion when you add the H2O2. Even this one, FeOH2 will convert to FeOH3 hydroxide precipitate, right? When you add the H2O2, right? So that will speed up, right? Plus 2 will convert to plus 3 in no time if you add H2O2. Now, actually, even without adding H2O2, these things will convert to the FeOH3, FeOH6, FeH2O6 3 plus as well as FeOH3. Even without adding H2O2, these things will eventually convert to these 3 plus forms, but it takes some longer time. But if you are adding H2O2, in no time, that conversion will happen, right? Just mention the colors as well there. So this one is actually, this kind is 3 plus form is, not 3 plus form is yellow brown. And the 3 plus hydroxide is kind of red brown. Actually, this is the iron rust, right? If you OH3, sorry, this is the iron rust, right? By taking off some water molecules from there, you will come up with the Fe2O3, which is the iron rust. That is the color, right? Red brown. So just put these colors as well in your table of ions, table of iron, right? Okay. Finally, you can see some H2O2 involvement in cobalt table as well. Yeah. So amine complex, the 2 plus form, right? Which is actually yellow brown. Can be converted to cobalt NH3 6 times 3 plus. Which is actually red brown. The color is red brown here. right? Yellow brown converted to red brown, right? It's aqueous solution, right? Sometimes it is referred to as orange brown as well. Anyway, that conversion, that oxidation will also can be done with the use of H2O2. Use of H2O2, right? So it can be done by a oxidation slowly, or can be done by H2O2 in a rapid way. So color these ones, see these ones, and color those at the cobalt table as well. Right now, that is the usage of H2O2, which will appear with each and every table other than the nickel and copper. With the nickel and copper, you won't see those, right? Because the plus than the plus two form, right? There are no higher oxygen states. There are no higher oxygen states than the plus two will appear with the nickel and copper, so that you won't see this kind of oxidations by H2O2 in nickel and copper tables. But with other elements, when it comes to other elements, you can see some great oxygen states are available than the plus two. So we can convert the plus two guys basically towards some great oxygen states with the use of H2O2 as an oxidizing agent, right? So that is the use of H2O2. Just color the species, see the reactions and color them at the corresponding spaces, right? Right, no? Right. What we have discussed up to now is actually the common things, the common reactions available with all of these tables, right? Okay. Now we will start the discussion of elements, the reactions involved in the D block elements, one by one, right? Let's start with the copper. Sorry, let's start with the chromium, right? Okay. Which is the first element we are going to discuss. But reactions of chromium. Right? Chromium is our 24th element. So it will come coming up with argon configuration and 4s1 3d5, no? Kind of special configuration appearing with the chromium, right? So let's discuss about the reactions involving chromium. Right, so we have a table there, right, indicating the reactions of chromium, right? Okay, let's discuss them one by one. These are the oxygen states available here, right? 0, +2, +3, and +6. Those are the major common oxygen states we can see with the chromium species, right? Let's start this discussion, right? So, chromium, the elemental state, right, is mentioned here, right? So this thing can be converted to the its nearest oxygen state, Cr2 plus aqueous ions, by just adding dilH plus, dil acid. right? So it will convert the chromium solid to CrH2O6 2 plus. This is Cr2 plus aqueous, right? Right. So what is the color there? The color is light blue. The color is light blue. We had discussed that thing earlier. Let's put that light blue there. Then basically that is this is not that much stable now. Right? This will be easily oxidized. This will be easily oxidized. Right? Easily oxidized. Even ArO2, even in air, that will be done. Right? And form the CrH2O6 3 plus. Will form CrH2O6 3 plus. That is actually Cr3 plus AQ, the neutral solution. Right? So what is the color of that thing? This is a neutral solution, right? This 6 of H2O ligands. That guy is coming up as a purple solution or violet in color solution. Right? Then actually we can convert the CrH2O3 plus, right, to CrCl6 3 minus by adding some excess of Cl minus. So let's say excess of HCl, Kong HCl also do so. So this guy's color is actually blue violet. Put that color. Right? Okay. Then to this hydroxide, to this aqueous solution, if you add some OH minus ions, add some OH minus ions, that can be provided by a strong base like NaOH or a weak base like ammonia, you can come up with the hydroxide precipitate, chromium hydroxide precipitate. So what is the color of the chromium hydroxide precipitate? Chromium hydroxide precipitate is blue green in color. Greenish blue. Right? So if you are adding some excess of OH minus, remember this reaction is very important. If you are adding some excess of OH minus, as this CrOH3 is amphoteric, it will convert to CrOH4 minus the hydroxide complex. It will convert to hydroxide complex. What is the color there? That is dark green. This dark green. One can say dirty green acid. Right? You remember this complex? So we had discussed this thing with amphoric patterns. Right? At the note number 2, we had discussed this thing as a special note. Right? Normally, amphoric guys will give you the hydroxide precipitate when you are adding little amount of OH minus, and when you are adding excess of OH minus, that hydroxide precipitate will dissolve to give you the hydroxide complex. No? Right? That same thing is possible with the chromium as well. Even though chromium is not considered as a amphoric metal, the chromium hydroxide is amphoric, so that chromium hydroxide is also capable of forming this hydroxide complex when you want to add some excess of OH minus, right? So that is this one, right? This is coming under infrared patterns, right? Also, so if you add some H plus ions to this solution, if you add some H plus ions to this solution, remember this is stable only in a very highly basic medium now. This is stable only in a very highly basic medium, right? Okay, so you have to supply some excess of OH minus, some excess. In excess, you have to apply to come up with this hydroxide complex, right? So if you are providing some H plus ions, right? If you are providing some H plus ions, you are providing some H plus ions, then what will happen? Right? One of these OH minus will be neutralized and come up to here, right? Some of the OH minus will neutralize and come up to this state, right? Clear? That is what happens if you are to acidify the hydroxide complex there, right? Because you are not maintaining a highly basic medium then, as you are acidifying the stuff. So OH minus will be neutralized so that this will convert to this stuff, right? So here OH minus, right? If you are to further add the OH minus, if you are further adding the OH minus to this hydroxide precipitate, so form, it will convert to this CrH2O 5Cl kind of a complex, right? That is what happens if you add some further H plus to this hydroxide precipitate, right? So that is actually the acidic medium Cr3 plus ions. Acidic medium Cr3 plus ions. So this is Cr3 plus, this is Cl minus. So altogether it is 2 plus with the charge, right? This is the acidic. This is the acidic Cr3 plus ions. Acidic medium Cr3 plus ions, right? So its color, you know, it is green. The color is green, right? The color is green. Clear? Right. That is the Cr3 plus acidic solution, right? Okay. So these are the major stuff you should know with the chromium 3 plus chemistry. Chromium 3 plus chemistry, right? We have another one, no? We have another one. So basically, you can convert this into its hydroxide. Its hydroxide. Sorry, this hydroxide can be converted to its oxide. Its oxide by a thermal decomposition, right? By a thermal decomposition. The hydroxides of moderately active metals can be converted to their respective oxides by thermal decompositions, right? So CrOH3 can be converted to Cr2O3, the respective oxide, by a thermal decomposition. That is also mentioned in your note. Just see that. What is the color there? CrOH3 is coming up as a dark green, so greenish black PPT, right? Clear? Right. What else? Actually, that is all with the chromium 3 plus chemistry. Let's move towards the chromium 6 plus chemistry, right? Now, this thing, the 3 plus guys, can be oxidized to chromium 6 by adding H2O2. By adding H2O2, this is very special reaction. By adding H2O2, you can convert this Cr3 plus to Cr6 plus. So basically, you are adding H2O2, and you know this is at a very basic medium, highly basic medium. So we can say this kind of basic medium addition of H2O2. So what will happen? You will form one of the two oxyanions of chromium there. That is CrO4 minus. That is CrO4 minus. One of the two oxyanions of chromium, which is yellow in color. Yellow solution. right now. Okay, then you can convert this yellowish CrO2 minus, you can convert this yellowish CrO2 minus, right? You can convert the yellowish CrO2 minus, right? Yellowish CrO2 minus can be converted to orange colored Cr2O72 minus, which is the other oxyanion of chromium. Chromium is it two oxyanions. That conversion actually can be done by just adding some dill acid, So remember, this guy is, what is the color of this thing? This guy is orange in color, Just color those, right? So CrO2 minus is the oxyanion which is stable in acidic mediums. In acidic medium, this thing lasts. So if you are adding some base to this one, it will convert to the chromate. That kind of a nice relationship between the, right. So if you are adding some H plus to this yellowish solution, it will convert to an orange colored solution, dichromate ions. If you are adding some OH minus ions to the orange color solution, it will convert to the yellow color solution, chromate ions, right. Such a nice relationship between the two oxyanions of chromium is there, right? It's clear, right? Then the last two reactions. This one. This is very common reaction. So Cr6 plus state can be reduced to Cr3 plus aqueous solutions. Can be reduced to Cr3 plus aqueous by just adding kind of a reducing agent in acidic medium. If you are to add some reducing agent in acidic medium, this will happen. The chromium plus 6 oxygen state will reduce to Cr3 plus aqueous ions, right? So as reducing agents, you can come up with anyone which are keen to get oxidized, right? So acidic dichromate is considered as a very strong oxidizing agent, right? So very keen to get reduced. So to do so, any kind of a species which is capable of getting oxidized, right? Participate in oxidation reaction can do so. So like H2S will oxidize to SO42 minus. Sorry, H2S will oxidize to sulfur when this one reduces to Cr3 plus aqueous. SO2 will oxidize to SO42 minus when this guy converts to Cr3 plus aqueous. Right? Cl minus, Br minus, I minus, those things will oxidize to, right, X2 forms when this guy reduces to Cr3 plus aqueous. Right? If you are coming up with NO2 minus ions, those will get oxidized to NO3 minus ions when this guy reduces to Cr3 plus. Right? So that acidic dichromate is considered as a very strong oxidizing agent. That is this reaction. Right? Very common reaction, actually very frequently asking situation, right? That is that thing, right? The last thing to consider here, this reaction. This is very important reaction again. Converting this dichromate to Cr2O3 solid, right? It is actually can be done by the decomposition of ammonium dichromate. This can be done by the decomposition of ammonium dichromate. Right? So I'll write that reaction here. So you better write it at the top of the page, right? This reaction is very important. When it comes to ammonium salt decompositions, the ammonium dichromate decomposition is very important, right? So decomposition of ammonium dichromate. This is the ammonium decomposition, right? Ammonium dichromate. right? It is looks like this. So ammonium dichromate will thermally decompose, to give you N2 gas, right? 4 of H2O gas and some Cr2O3 solid. So this decomposition is very important, Lamai, because here you will observe some orange color stuff appeared initially. The orange color solid appeared initially will convert to kind of dark green residue, right? Greenish black residue, right? So that is very important, right? This is actually this is the only instance. This is the only instance where you observe. This is the only instance where you observe kind of a solid residue by a ammonium salt decomposition. This is the only instance you observe kind of a solid residue by a ammonium salt decomposition. So that is very important in reaction schemes, right? Study that, right? So put this note as well, but in your note, right? So that is mentioned here. Not all the dichromates, but ammonium dichromate decomposition will ultimately provide you the Cr2O3. That kind of a reduction also can be seen with that thing, right? No? Okay, just complete the chromium reactions. Right now, let's discuss the chemistry of manganese. Right? We are done with the chromium now. Let's go towards the manganese. Manganese reaction table, right? Okay. Right now we are up to the manganese. Reactions of manganese. Emit. So it is coming up as it is the 25th element. That means after the argon group it is coming up as 4s2 3d5. No? It is manganese, right? Okay. So it will also show some few oxygen states, right? We start with the +2, right? And you'd observe the +4 oxygen state, right? +4 oxygen state, +6 oxygen state, as well as the +7 oxygen state with the manganese, right? +4, +6, and +7 are there as common oxygen states or major oxygen states for manganese, right? Let's discuss the reactions involving manganese, right? Okay. So you could think of the manganese metal, and it can be oxidized to Mn2 plus aqueous solution, or one can say towards MnH2O6 2 plus. This is the Mn2 plus aqueous solution. the color of that thing is pale pink, or one can say colorless. That oxidation can be done by addition of dill acid. We had discussed this thing. So as a dill acid, you can come up with dill HCl, dill H2SO4, those things, right? Then with the MnH2O6 2 plus, it can be converted to its chloride complex, right? With all of these D block metals, we can form the chloride complex, no? Complexes. No? So chloride complexes normally come up with 4 chlorine ligands. So normally those are yellowish. So manganese chloride complex coming up with a yellow green situation, or greenish yellow. Right? So that can be formed by adding some excess of chloride ions. Complexes can be formed by adding excess of those ions, right? So excess of Cl minus, or one can say conc HCl or excess HCl can provide that, right? Then we can convert the Mn2 plus aqueous solutions to their to its hydroxide, to its hydroxide, to its hydroxide by providing some OH minus ions to the medium. So all these D block cations will form their respective hydroxides when the OH minus ions are provided to the medium. So MnOH2, what is the color there? The MnOH2 coming up as a cream kind of a color, or one can say yellowish white. Right? And remember, all of these hydroxides can be dissolved back to the aqueous ions, can be dissolved back to the aqueous ions by acidifying the medium. Dill acid will do so. You know that if your precipitate is not containing a strong acid anion, if your precipitate is not containing a kind of a strong acid anion, then those precipitates will dissolve to come up with the aqueous ions with the addition of a dill acid, right? That reaction is involved here, right? Okay, done. Then we have discussed this reaction as well. This is a special reaction done by the H2O2 or air oxidation. So ArO2 will slowly oxidize the manganese hydroxide to MnO2, but if you have to add H2O2, some fast conversion will occur and the MnOH2 will convert to MnO2, convert to MnO2 solid, right? What is the color there? So MnO2 solid is brownish black, brownish black. Right now? Okay. Then we could think of the two species appearing with the +4 and +6 oxidation states of manganese. Actually, those are the manganate and permanganate ions. The permanganate ions, you know about that thing, the KMnO4 permanganate ion, which is +7 oxidation state of manganese, and the other one is the manganate, MnO4 2 minus, which is the +6 oxidation state of manganese. Right? So actually, we know a reaction. We know a reaction between these three guys, involving these three guys. What is that? Basically, if you are thinking of decomposition of, or one can say, yeah, the thermal decomposition of KMnO4. If you think of thermal decomposition of KMnO4, you may have done this to get some O2 gas in O levels. Remember that? To produce O2 gas, what you have done in O levels is actually decomposing the KMnO4, right? So if you decompose the KMnO4, right? you'd observe, you'd observe kind of a reaction involving potassium manganate, MnO2, and NO2, right? So this is the thermal decomposition of KMnO4. Yeah, you find the plus 7 oxoanion, plus 6 oxoanion of manganese, as well as plus 4 oxide of manganese, right? So if you are to put some water, if you add some water to this test tube, if you add some water to this test tube, you will observe kind of a residue, black color residue, and a solution. If you add some water to this test tube after O2 is released, if you add some water to this test tube, right, you'd observe kind of a solid residue, MnO2, and kind of aqueous solution which is greenish color, dark green in color, right? So remember that. So MnO2 is brownish black, while the K2MnO4 is dark green in color. Dark green in color. The solution is dark green in color. That is because of the formation of MnO4 minus. Right? That kind of observation can be seen if you do that experiment and add some water to the solution. Right? So what I need to emphasize here is the color of MnO4 minus ions. So basically, the color of MnO2 minus ions are considered as what? Considered as dark green. Dark green. Right? And you know the color of KMnO4, the MnO4 minus ions. Those are purple in color, violet, purple in color. The color of KMnO4 is due to the presence of MnO4 minus ions there. Colors of the aqueous solutions are appearing because of the presence of ions involving D elements, right? So the color of KMnO4 is due to the presence of MnO4 minus ions, not due to the K plus ions, right? Okay. S and P block cations are S and P block ions are colorless. Any ion involving only the S and P block elements are colorless in aqueous solutions. Colors of aqueous solutions containing ions appears due to the presence of D block elements, right? Okay, right. So these three are involving with this reaction, and then we can observe another kind of reactions if you add some reducing agent to KMnO4. If you add some reducing agents to KMnO4, that thing will reduce to form Mn2 plus ions or to form the MnO2 ions. So if you add some reducing agent, if you add some reducing agent to these MnO4 minus ions, it will reduce to Mn2 plus ions if you are adding the reducing agent in acidic medium. But if you are adding the reducing agent in basic medium, the MnO4 minus ions will convert to MnO2. So in your reaction tables, this is the one which is mentioned as H plus zinc. So normally to symbolize kind of reducing agent, we use that zinc, that symbol, right? So zinc is used as it is a metal. So metals are the best guys to get oxidized. Metals are the ones which are very keen to get oxidized. So we can say those are the best reducing agents, right? To indicate kind of a reducing agent, we indicated there the zinc. Not only zinc, we can come up with any kind of reducing agent there for those reactions, which are mentioned by H plus zinc, right? Acidic medium, reducing agent, right? Okay. So SO2, it can get oxidized to SO4 minus. H2S, which can be get oxidized to sulfur, Cl minus, which can be get oxidized to Cl2, like that, NO2 minus, right? Okay, any kind of reducing agent can be used to do these changes, to convert the manganate, permanganate to Mn2 plus, or to convert the permanganate to MnO2. Those are the those two reactions, right? Okay, after that, let's discuss a bit more stuff with this reaction scheme. Now, let's discuss how to produce this ion, how to come up with the MnO4 minus. The one way of producing that ion is just the decomposition of KMnO4, right? This is just another way. So basically, you can get to this one. You can get to this one by maintaining a highly basic medium. By maintaining a highly basic medium. Basically, you can see the trend here now. So if you are to reduce the MnO4 minus in an acidic medium, that guy will reduce to plus 2. If you are to reduce the MnO4 minus in an acidic medium, that guy will reduce to plus 2. If you reduce the MnO4 minus in a neutral medium, in a neutral low basic medium, slightly basic medium, it will reduce to plus 4. It will reduce to plus 4. So if you are to reduce this MnO4 minus in a highly basic medium, what happens is it will just reduce to plus 6. It will just reduce to plus 6. That is what happens then, right? If you are doing the reaction in a let's say concentrated NaOH medium, if you have to do this reaction in a concentrated NaOH medium, that is what happens. Concentrated NaOH medium. So there, the OH minus ions of NaOH will oxidize to O2, while this guy will reduce, right? Your OH minus ions there will oxidize to O2, while this one get reduced. So some trend is there, right? So if you are to reduce this one in an acidic medium, this reduced to plus 2, right? Gaining more electrons in an acidic medium. If you are to reduce this thing in a neutral low basic medium, slightly basic medium, it reduced to plus 6, plus 4, just taking only 3 electrons from the other species. But if you are to do the reduction in a very highly basic medium, basically like pH 12 onwards, you would observe the presence of the reduction of MnO4 minus. So remember, this is stable in very highly basic medium. Stable in highly basic medium. Right? So basically, the pH should be greater than 12. Very highly basic mediums only, that is stable, right? So that can be produced even by adding conc NaOH there, right? So if you add some liquid KOH to this thing as well, you will come to that state. So if you are to basify the MnO2, which can be there in a slightly basic medium. So if you are to increase the basic nature by adding kind of liquid KOH, that thing will also oxidize to here. So this one is the anion which is stable in a very highly basic medium, right? There what happens is the oxygen, the dissolved oxygen, right? Dissolved oxygen in air will convert to OH minus, right? Kind of a kind of reduction happens there while this get oxidized, right? Okay. So that is the other method of forming MnO4 minus, right? By maintaining a highly basic medium, right? No? Okay. Then, as we know that this guy is stable in a very highly basic medium, right? If you add some acid to this thing, the stability decreases. It becomes unstable in an acidic medium, so it will dispronate. it will dispronate to give you the MnO2 and the MnO4 minus. It will dispronate by addition of an acid, as that is stable only in a highly basic medium. By addition of an acid, just few drops, even at pH 9, pH 10, even at pH 10, this will dispronate by addition of H plus, because it is stable only in a highly basic medium, right? So this is kind of a dispronation. That reaction should be also known, right? Dispronation, right? Okay, so these are the old reactions you should know with the manganese chemistry, right? So just color those things and study the reactions with the manganese chemistry, right? Just write this thing as well, right? Okay, so that's it for the manganese chemistry. Just copy the board. Right, Lamane? So let's discuss the chemistry about iron, right? The chemistry of iron. Let's go towards that, right? Okay. So now we are going to discuss about the chemistry or the reactions related to iron, right? So reactions of iron. So iron is Fe. So configuration is, after the argon configuration, it is 4 is to 3d6, no, 26 atom. So iron is with only two oxygen states, major two oxygen states, other than the zero oxygen state, right? Okay. Other than zero oxygen state, you have +2 and +4 oxygen states for the iron, right? So +2 and +3. Those are the common oxygen states available with the iron, right? This is us about those reactions involving iron, right? The first reaction is actually converting the iron to its 2 plus aqueous solution. So Fe can be converted to FeH2O6 2 plus aqueous solution by the addition of a dilyl acid, dilyl H2SO4, dilyl HCl can be used for that, right? So the FeH26 aqueous solution is actually green in color, right? Then so form FeH2O6 2 plus can be converted to its chloride complex FeCl4. Chloride complex is normally coming up with 4 chlorine ligands. This is -4, 4 of Cl minus -4 and +2 here. So altogether it is going to be S2 minus, and its color is yellowish. The chloride ligands coming up with chloride complex is coming up with yellowish color. That conversion can be done by the addition of a excess of Cl minus ions. So excess of Cl minus ions, or one can say concave Cl or excess HCl, can be used to convert this into here. And then, right, you could observe the hydroxide precipitate formation if you add some OH minus ions, or if you are to basify the medium. That can be done by NaOH or even by aqueous ammonia. By providing some OH minus ions, the Fe2 plus aqueous solution will convert to its hydroxide precipitate. What is the color of that thing? So the hydroxide precipitate is normally following the colors of aqueous solutions. So as this one is green, this one is dark green. This one is dark green. Right? And these hydroxide precipitates can be converted again to the aqueous solution by acidifying the medium. So by acidifying, the OH minuses will neutralize with the formation of H2O. The H plus you are adding will neutralize the OH minuses appearing here and coming up as H2O, so that this cation, Fe2 plus cation, will come to the solution. Right? Fe2 plus aqueous can be written as FeH2O6 plus, right? Okay, aqueous. Right. And the thing you should know is these two guys, both of these guys will convert to the 3 plus forms. Will convert to 3 plus forms when those are allowed to expose to air. When these are allowed to expose to air, both of these guys will convert to 3 plus forms. So Fe H2O6 2 plus aqueous will convert to FeH2O6 3 plus aqueous. Even this one will convert to FeOH3 solid. Right? By air oxidation. Slowly that conversion happens. But if you are to add some H2O2 to this solution, that will convert rapidly in no time. If you are to add H2O2 to this Fe2 plus, it will convert to Fe3 plus in no time. This as well. This kind of usage of H2O2. Right? And we know that Fe3 plus aqueous can be converted to its hydroxide by adding some kind of OH minus ions to the solution, and this HCOH3 will be converted to its aqueous ions by acidifying the medium. By adding an acid, these OH minus ions will be neutralized and Fe3 plus ions comes to solution. Right? Those are normal stuff. Still, we haven't discussed any new reaction there. Even this one is capable of converting to its chloride complex. Chloride complexes are coming up with 4 chlorine ligands. The charge is -4 as 4 Cl minuses are there, and +3 here, so that it is -1 the charge. This is also yellowish. Chloride complexes are normally coming up with yellow color. You know the colors of these two guys, right? So this guy is actually reddish brown, and this guy is yellow brown. Right? And you can reduce these terms to 2 pluses if you add some reducing agent there. Right? If you add some reducing agent, these guys can be converted to if it becomes acid. Right? Okay. Right. These are the common reactions you can see with each and every table. Let's discuss the more important, special, the characteristic reactions. involving characteristic reagents for iron, right? Basically, we are going to discuss about 4 characteristic reactions with 4 characteristic reagents, and those are only appearing with the iron table, only appearing with this table. We won't see these 4 reactions now I am about to discuss with any other table, right? So that we can consider these reactions as characteristic reactions, or one can say with the use of characteristic reagents. Let's discuss the 4 characteristic reactions or characteristic reagents can be used to identify the ions, right? The first one, the first one. So basically, to identify the Fe3 plus ions, you can use salicylic acid, salicylic acid, salicylic acid. This is kind of characteristic reagent for Fe3 plus. In our syllabus, salicylic acid is added only to identify the Fe3 plus, only to see whether the Fe3 plus is present or not. Right? So we can say we can consider it as a characteristic reagent. So if salicylic acid is added to Fe3 plus aqueous solution, right? If Fe3 plus was there, if you are adding salicylic acid to your solution, if Fe3 plus is there, you will ultimately observe kind of a purple color solution. Purple color solution. When you are adding salicylic acid to your solution, if no purple color is observed, that means Fe3 plus is not there. If a purple color observed, you can say Fe3 plus is definitely present there. So salicylic acid is kind of a characteristic reagent, and this is going to be a characteristic test for Fe3 plus, done to identify or done to comment whether the presence or absence of the Fe3 plus. Second characteristic reaction, done only to identify the or confirm the presence of Fe3 plus, is the test with SCN minus ions. Test with SCN minus ions. So any form of SCN minus ions can be added. It could be in the form of ammonium thiocyanate or potassium thiocyanate, sodium thiocyanate. Any kind of SCN minus ions could be provided here. So if Fe3 plus was there in your solution, test solution, addition of SCN minus ions will give you a blood bread compound. So we can write that compound as FeSCN compound, blood bread compound, right? So right, if it is writing like this, it's going to be SCN minus and Fe3 plus, so charge is plus 2, right? Okay. So according to amount of SCN minus you are adding, right? The chemical formula of this blood bread compound could vary, right? The chemical formula of this blood bread compound would vary, right? So this is also blood bread. That could vary according to the amount of SCN minus ions you are adding, right? If you are adding more SCN minus ions, right? If you are adding more SCN minus ions, right? You could come up with SCN2 as well. You could come up with SCN2 as well. Then this charge is going to be SCN minus twice, minus 2, like this. Or if you are adding more further SCN minus ions to the solution, you could come up with FeSCN3 as well. Then no charge will appear. So no charge will appear means it's a solid. So you could come up with blood bread aqueous solutions or blood bread solids if you add some SCN minus ions. So anyway, any compound, all the 3 compounds are blood red in color. So we can say you can obtain blood red colored compounds if you add some SCN minus. According to the amount of SCN minus you are adding, it could be with 1 SCN part or 2 SCN parts or 3 SCN parts. If you are with a charge with your complex, then those are aqueous solutions, blood-red aqueous solutions. If you are not with the charge there, then it is kind of a blood-red precipitate. Clear? Right. Those are two characteristic tests can be done to identify the presence of Fe3 plus ions. Right? Both are blood-red, right? Here the blood-red PPT. Here blood-red solution. Right. Let's discuss the other two characteristic reactions involving in the ions. Right. The third one. Third characteristic reaction I'm going to discuss. That is also to identify the presence of Fe3 plus ions. So that is referred to as the addition of potassium ferrocyanide solution. Addition of a potassium ferrocyanide solution. See, what is the theory behind that thing? So this is referred to as the potassium ferrocyanide. K4FeCN6. This is referred to as the potassium ferrocyanide. Right? Why it is said so? So basically, if you are to come up with the oxygen state here with the iron, so you are coming up with -6 as these are Cn minus ligands, -6 the charge, +4 the charge here, this is +4, is -6 coming from here. So this guy's charge will be +2. This guy's charge will be +2. +2 form of iron is referred to as ferrous. Fe2 plus is ferrous. Fe3 plus is ferric. Fe2 plus is ferrous. Fe3 plus is ferric. So the +2 form of iron is referred to as the ferrous. So this compound is referred to as the potassium ferrous cyanide. We are not writing like this. Potassium ferrocyanide. Ferro coming from the ferrous. Ferrous. Ferro. So this is referred to as the potassium ferrocyanide. Potassium ferrocyanide. Why ferro? Because it contains ferrous. +2 form. Ferrocyanide. Remember that. You should be able to write the reagent properly. Right? With potassium ferrocyanide, if you are to add Fe3 plus ions, ferric ions to ferrocyanide, if you are to add some ferric ions, what happens is you will observe a formation of blue PPT. To the Fe2 plus complex, if you are adding Fe3 plus ions, you would observe a blue PPT. And you should know the chemical formula as well. So writing the chemical formula is not that much hard. What you need to do is just exchange the valencies. This is Fe3 plus, this complex is coming up with 4 minus. So this is +4. This complex is coming up with 4 minus. So 4 minus and Fe3 plus. So exchange the valencies to come up with the compound. So FeCN6, this coming up with 4 minus. So exchange of valencies is coming with 3 plus. So this is your blue colored compound. This blue compound, blue colored solid, blue PPT. Right? So with the ferrocyanide, you get a blue PPT if Fe3 plus the ferric ions were there in your test solution. Right? Okay? Right. Let's discuss about the next test as well. These two tests are kind of with a similar kind of pattern. Right? If you are adding ferrocyanide, if ferric ions were there, you get a blue PPT. Right? We'll discuss the next test, which is actually done for the Fe2 plus ions. I earlier said there are 4 characteristic tests. To identify the presence of ions. We have discussed three so far. This one, and this. The fourth one is actually with the use of a reagent called as potassium ferrocyanide. Potassium ferricyanide. Ferricyanide. So ferri term coming up with the ferric. That ferri name coming up with the ferric. So its formula is this. Here you can see minus 6 is appearing here as 6 of Cn minus ions. Plus 3 is appearing here, so that this guy's charge is going to be plus 3. Plus 3 for here, minus 6 for here. So this should come up with plus 3. So this reagent is referred to as potassium ferricyanide. As ferric is there, is ferricyanide. Ferricyanide. So if you have to add some ferrous ions, to this ferricyanide solution, if you add some ferrous ions, Fe2 plus ions to ferricyanide solution, then you would observe a blue PBT. Right? Then you would observe a blue PBT. So what is the formula there? The formula is like this. So you have 3 of K plus ions, 2 of those will be replaced by this, replacing charges there, right? So you will ultimately end up with K Fe, 2 of K plus ions are replaced by Fe2 plus, and the compound FeCN6. Right? It's a blue PBT. Right? You see? The thing here is, Lamai, the blue PBT is formed when you are adding the opposite ion, the other ion, than the ion inside the complex. If you have this ferric ion inside the complex, when adding ferrous ions, you get the blue PBT. If you are with ferrous cyanide inside the complex, when adding Fe3 plus ferric ions, the other ion will give you the blue PBT. That is how you study this thing. Right? Here, the exchange of valencies will give you the compound. Here, kind of ion replacement. Right now? Okay. So those are the 4 characteristic tests. 3 were done to identify the Fe3 plus, and the other was done to identify the Fe2 plus. Right? Okay. And you have 2 of these things as well. That is not that much of use. Right? Just to complete the note, you have those 2 things as well. Not that much worry about this 2 stuff, right? Which is the white PPT and brown PPT, right? You have white PPT and brown PPT. But normally the questions will be asked from these 2. This is what happens if you are to add Fe2 plus 2 ferrous to ferrocyanide. This is what happens if you add some ferric to ferricyanide. Don't think of that thing that much, right? So the questions will be asked from these 2 reactions as well as these 2. Those are the 4 characteristic reactions, 1, 2, 3, 4, to identify these presence of ions, right? Okay, so just complete this note on ion. Right, no? Okay, so let's move to the Next one, the chemistry of cobalt. One can say the reactions involved in the cobalt species. Right? Let's go towards that. Right. Reactions of cobalt, right? Reactions of cobalt. So cobalt is your 27th element, no? 27th element. So one can say this is the argon. After argon, 4 is to 3d7, no? 27th element, right? Right. This is just the chemistry or the reactions involved in the cobalt species. So with cobalt, you can observe only two oxygen states. So other than the oxygen, you have other than the zero oxygen state, you have the +2 and +3. The two major oxygen states with cobalt. Right. Okay. Let's discuss the reactions there with cobalt. Right. Okay. So we can think of the cobalt oxidizing with the use of a dill acid. So cobalt is situated above hydrogen active series, so that addition of a dill acid, dill H2SO, dill HCl, will convert the cobalt metal to its salt. That means cobalt 2 plus ions. So it can be written as cobalt H2O6 2 plus form. What is the color there? That guy is pink in color. So with cobalt as well, you can think of forming the chloride complex with the excess addition of Cl minus ions. So one can say excess of HCl that can be divided by conc HCl as well. So that will convert the cobalt to cobalt Cl4 2 minus. This cobalt chloride complex is very special now. Due to two reasons, this one is very special. The first reason is actually this is kind of a cobalt. This is kind of a cobalt chloride complex. This is kind of a chloride complex, right? Which is actually coming with a color other than the yellow. So normally in our syllabus, most of the chloride complexes, if they are colored, those are coming up with yellowish color. But only two chloride complexes are there. Only two colorful chloride complexes are there with colors with colors other than the yellowish color. One of those is cobalt, right? What is the color there? It is not yellowish. Its color is blue. Its color is blue. Blue color solution, right? That is one special thing with the cobalt chloride complex. It's a colorful chloride complex which is with a color other than yellow, which is blue then, right? The other factor, the second importance of this complex is actually forming this cobalt chloride complex involving a double arrow reaction. That means you can convert this thing to here by addition of XCl minus. Then you can convert this thing to here with the addition of water. with the addition of water. Not all the chloride complexes are capable of converting again to the aqueous solution by the addition of water. Right? Not all the chloride complexes are capable of doing this, converting again to the water, converting again to the aqueous complex by the addition of water. Only two such chloride complexes are there. One is cobalt. One is cobalt chloride complex. The other one is coming up with the copper chloride complex. So those are the only two chloride complexes which can be converted again to the aqueous solution, to the aqueous cations, right? So actually this text has been done in your O levels as well. In your O levels, if you have to remember, there was a test called as cobalt chloride test. There was a test called as cobalt chloride test. Right? In which kind of a purpose you had used the cobalt chloride test? Do you remember that? Yes. Actually, cobalt chloride test is used to identify the presence of water molecules, presence of water in your samples. To comment whether water is present or not in a given sample, you had used cobalt chloride. Normally in the form of a filter paper. So normally what you do is you dip a filter paper in a cobalt chloride solution so that it will turns to blue. Filter paper turns to blue, and then if you leave that filter paper in your test sample, if that blue color filter paper converts to pink color, we can say the water is there in the sample. The water is there in the sample. If the blue color cobalt chloride won't convert to the pink color, that means water is not there in the sample. So to identify the presence of water in your small ages, in your O levels, you had used the cobalt chloride test, right? That is actually this one. Right now? Okay. Next thing. So, like in all the other metals, you can convert the cobalt 2 plus aqueous to its hydroxide, to its hydroxide precipitate, to its hydroxide precipitate, right? So, cobalt hydroxide precipitate, what is the color there? So, it will follow the color of aqueous solution, right? That is pink, pink in color. So, this can be done by supplying some OH minus ion solution. Can be supplied by adding some strong base as well as aqueous ammonia as well, right? So these hydroxide precipitates can be easily converted to the aqueous ions again by just acidifying the precipitate, right? By adding H plus, as this one is kind of a precipitate not containing an anion coming from the strong species, it will definitely dissolve to give you the aqueous metal cation, right? Okay, that is the normal reactions, right? The next few reactions we're supposed to discuss here. So Lamai, you can convert this cobalt hydroxide to its cobalt amine complex its cobalt amine complex if you add some ammonia to this one. If you add some ammonia to this one, you add some ammonia to this one, aqueous ammonia to this one, this cobalt hydroxide precipitate will dissolve as it is coming up as a D7D10 cation. When you are with a D7D10 cation here, it is a D7D10 cation, right? D7 configuration is there after releasing the 2 electrons here. Cobalt 2 plus is coming up with a D7 configuration. So if you are with a D7, if you are with a cation with D7 D10 configurations, excess addition of NH3 to the hydroxide will convert that into the amine complex. So you can form the cobalt amine complex by adding some ammonia to the hydroxide precipitate. Cobalt amine coming up with 6 amine ligands, right? 6 amine ligands. And what is the color of that thing? The cobalt amine complex is yellowish brown, yellow brown, right? So if you can add the conc ammonia to this thing, directly you can convert to its amine complex as well, right? If you add in dill ammonia, you have to add in excess to go to here and then here. But if you add in conc ammonia, if you add in conc ammonia to the aqueous solution, that means you are supplying some excess of NH3. You can directly convert the aqueous solution to the amine complex, right? Right. Those are still we are discussing the normal trends, right? Then this one, this cobalt amine complex, this cobalt amine complex can be converted to the 3 plus amine complex by adding H2O2. The oxidation will slowly do that thing. ArO2 will slowly do that thing. But if you add H2O2, you can convert the cobaltamine complex to the cobaltamine 3 plus. Convert the cobaltamine 2 plus complex to cobaltamine 3 plus complex in no time. Right? Cobaltamine 3 plus. What is the color there? So basically, this complex is actually red brown in color. Red brown in color. Red brown in color. This complex is red brown in color. Right? But practically, if this thing is done with the air oxidation, if this thing is done with the air oxidation, not using the H2O2, if this is done with the air oxidation, just allowing this thing to oxidize to this, right? Then practically we would observe kind of a orange brown color when forming this one. Because this is yellowish brown, and if that conversion happens very slowly, when part of this thing converted to this, both the stuff are at the system, red brown thing and the yellow brown thing are at the system. That means you will observe a mixed color, orange brown. So formation of this thing, right, can be observed as kind of orange brown mixture as well. So we can say in some questions this thing is appeared as kind of orange brown mixture. So red brown, no, orange brown. Both can be used in questions. The color of cobaltamine 3 plus. Right now? Okay. So another reaction is to be there, is there to be concerned, written there. So let's discuss about that thing as well. That is very rare reaction, Lavai. Normally that is not going to be asked in your A levels, but one of the research books, singular or the English, one of the research books contain this thing. So we have to know about that thing as well. If you had some excess, you had some excess of OH minus to this thing, you had some excess of OH minus to this thing, it says will produce this special complex cobalt OH 4 times complex. OH minus, that means minus 4 is there, and cobalt 2 plus is there altogether. So it should be 2 minus, 2 minus should be the charge. Right? And that complex is actually is with a dark blue color. Is with a dark blue color. This complex is with a dark blue color. This color that I said, dark blue in color. Right? So this is all you should know about the cobalt chemistry. Right? It's all about the cobalt chemistry. Just complete the table. Just complete that. Right, another one. So let's wind up the session for today with the cobalt chemistry. Let's meet with another session to discuss about the nickel and the copper chemistries as well as the questions appearing in your tute. Right? Okay, so that's all for today. Goodbye then. See you next week.